Welcome to CUI Learning Channel. In this lecture, we will discuss the corrosion under insulation, CUI. Description of damage. Corrosion of piping, pressure vessels, and structural components, resulting from water trapped under insulation or fireproofing, as illustrated in figure. Example of corrosion under insulation: of carbon steel level brittle after insulation removal. Affected materials: carbon steel, low alloy steels, 300 series stainless steel, 400 series stainless steel, and duplex stainless steels. Critical factors: temperature, duration of wetting, design of the insulation system, insulation type, and environment are critical factors. Corrosion rates increase with increasing metal temperature, up to the point where the water evaporates quickly. CUI can occur on equipment operating at virtually any temperature of practical concern in refining. For carbon steel, low alloy steel, and 400 series stainless steel equipment, operating between 10 degrees Fahrenheit and 350 degrees Fahrenheit. For 300 series stainless steel, where chloride stress corrosion cracking is the concern, refiners generally focus on the temperature range of 140 degrees Fahrenheit to 350 degrees Fahrenheit. For duplex stainless steel, where chloride stress corrosion cracking is the concern, refiners generally focus on the temperature range of 280 degrees Fahrenheit to 350 degrees Fahrenheit. Poor design or installation of insulation systems that allow water to become trapped will increase corrosion under insulation. Equipment that operates below the water dew point tends to condense water on the metal surface, thus providing a wet environment and increasing the risk of corrosion. Insulating materials that wick moisture can hold water and be more prone to causing extensive corrosion under insulation. Insulating materials that dry out slowly can be more prone to causing extensive corrosion under insulation. Cyclic thermal operation or intermittent service can increase corrosion. Damage is aggravated by contaminants that may be leached out of the insulation, such as chlorides. Plants located in areas with high annual rainfall or warmer marine locations are more prone to corrosion under insulation than plants located in cool and dry or warm and dry locations. Environments that provide airborne contaminants such as chlorides, for example from marine environments or cooling tower drift, or sulfur dioxide, for example from stack emissions, can accelerate corrosion. Affected units or equipment. All insulated piping and equipment are susceptible to corrosion under insulation. under conditions noted in previous slides. Even on piping and equipment where the insulation system appears to be in good condition, and no visual signs of corrosion are present, as illustrated in figure. Equipment designed with insulation support rings welded directly to the vessel wall, for example with no standoff, can be susceptible, particularly around ladder and platform clips, lifting lugs, nozzles, and stiffener rings, as illustrated in figures. Piping components and locations that are particularly susceptible include dead legs, vents, drains, and other similar items, pipe hangers and other supports, valves and fittings with irregular insulation surfaces, bolted on pipe shoes, steam tracing tube or heat tracing wire penetrations, as illustrated in figures. As illustrated in figures. The first few feet of a horizontal pipe run adjacent to the bottom of a vertical run, and locations where insulation plugs have been removed to permit piping thickness measurements on insulated piping and equipment are a potential source of water ingress. Appearance or morphology of damage. Carbon steel and low alloy steels are subject to corrosion, having a rough, uneven, somewhat pitted appearance, usually covered with a loose, flaky, non-protective scale attached. The corrosion will be localized to wherever the metal has been kept wet by wet insulation, as illustrated in figures. T in a 1000 sig ethylene line before insulation removal, and close-up of T corrosion under insulation of a T after insulation removal. In some cases, the corrosion can appear to be carbuncle-type pitting, usually found under failed coating. 300 series stainless steel are subject to stress corrosion cracking if chlorides are present, while the duplex stainless steels are less susceptible. Stress corrosion cracking failures have occurred in duplex stainless steel due to corrosion under insulation, as illustrated in figure example of stress corrosion cracking. 300 series stainless steel and duplex stainless steel are subject to pitting and crevice corrosion. Prevention, mitigation. Since most construction materials used in refining are susceptible to corrosion under insulation damage, mitigation is best achieved by applying an appropriate coating to the equipment prior to insulating. Insulation, insulation jacketing, sealants, and vapor barriers should be properly maintained to prevent moisture ingress. Thin aluminum foil wrapped on stainless steel piping and equipment beneath the insulation can provide an effective barrier. Partly due to the galvanic effect of the aluminum in preventing chloride stress corrosion cracking in stainless steel. Careful selection of insulating materials is important. Closed-cell foam glass materials will hold less water against the vessel pipe wall than mineral wool and potentially be less corrosive. Insulation with added corrosion inhibitor is available. Low chloride insulation should be used on 300 series stainless steel to minimize the potential for pitting and chloride stress corrosion cracking. As illustrated in figures. Examples of closed-cell foam glass materials. Inspection and monitoring. An inspection plan for corrosion under insulation should be a structured, systematic approach starting with prediction and analysis. Per the CUI planning information contained in API 510, API 570, and API 583. The inspection plan should consider history of CUI leaks, operating temperatures that may give rise to corrosion under insulation, type and age condition of coating, and type, age, and condition of the insulation material. Although external insulation may appear to be in good condition, corrosion under insulation damage may still be occurring in isolated areas, not thought to be susceptible. The owner-user generally determines the extent of corrosion under insulation inspection, including the extent of insulation removal for inspection. Based on inspection and corrosion under insulation history and other factors as described above. Common areas of higher corrosion under insulation concern in process units are high moisture areas such as those downwind from cooling towers, the drift zone, near steam vents, under deluge systems, exposed to acid vapors, or near supplemental cooling with water spray. Utilize multiple inspection techniques to produce the most cost-effective approach, including guided wave testing, RT, including profile, density, flash, radiometric profiling, real-time, computed, and digital. Pulsed eddy current, neutron backscatter, for identifying wet insulation, and infrared thermography imaging, for identifying wet insulation. As illustrated in figure. Example of guided wave transducer arrays, signal representation, and results. As illustrated in figures. Profile radiograph of corrosion under insulation damage on an insulated small diameter pipe. N. Photo of a flash radiography system. 4. Pipe profiling to detect wall thinning due to corrosion. As illustrated in figure. Example of Radiometric profiling display and system. As illustrated in figures. Example of real-time radiography system. Representation of corrosion under insulation in left, and a silhouette display of corrosion under insulation, right. As illustrated in figures. Examples of Neutron backscatter and a pulsed eddy current system. As illustrated in figures. Examples of infrared thermographs showing areas with wet insulation, in red. Related mechanisms to corrosion under insulation are atmospheric corrosion, oxidation, oxygenated water corrosion, concentration cell corrosion and chloride stress corrosion cracking. Summary. Description. A corrosion of piping, pressure vessels and structural components resulting from water trapped under insulation or fireproofing. Localized pitting corrosion and/or localized loss in thickness. Often appears as loose, flaky scale covering the corroded component. Corrosion can appear to be carbuncle-type pitting. Temperature range: 10 degrees Fahrenheit to 350 degrees Fahrenheit for carbon steel, low alloy steel, and 400 series stainless steel. 140 degrees Fahrenheit to 350 degrees Fahrenheit for 300 series stainless steel. 280 degrees Fahrenheit to 350 degrees Fahrenheit for duplex stainless steel. Affected metallurgy: carbon steel, low alloy steels, 300 series stainless steel, and duplex stainless steels. Prevention. Mitigation is best achieved by using appropriate paints, coatings and maintaining the insulation sealing. Vapor barriers to prevent moisture ingress. Inspection methods: VT, UT, and/or a pit gauge. GWT. RT, including profile, density, flash, radiometric profiling, real-time, computed, and digital. PEC. Neutron backscatter, for identifying wet insulation, and infrared thermography imaging, for identifying wet insulation. Practice time. Question number 1. Which of the following environments factor influences on CUI? Answer is A. Question number 2. CUI mitigation is best achieved by Answer is A. Question number 3. The following materials used to prevent CUI are made of. Answer is D. Question number 4. The recommended technique for identifying wet insulation and potential CUI is. Answer is D. Question number 5. Regarding CUI inspection of externally insulated vessels, the susceptible temperature range for austenitic stainless steel refers to which of these operational temperature ranges? Answer is D. This lecture is prepared by Samir Saad and this is his profile. Thanks a lot for watching and please waiting us for the next lecture.